Okay, so welcome everyone for today's quantum space-time seminar. Today we are very happy to have Jan de Boer from University of Amsterdam, and he's going to tell us about quantum gravity meets statistical physics. Over to you,
Jan. Yeah, thanks. It's a pleasure to be in my room with you. Normally I say it's a pleasure to visit, but that's not applicable. Yeah, so in this seminar, I'd like to explain some ideas that we're developing right now that have to do with what else quantum gravity. And so we'll see, I called it quantum gravity meets statistical physics, but I could have chosen different titles as well, I suppose. This talk is based on some work that I did last year together with Alex Bellin and another paper with Pranjal Nayak and Julian Sonner. But there's also a bunch of work in progress with various collaborators in various collaborations, which includes a PhD student, Diego Lisca, a postdoc, Tarek Anous, another postdoc, Igal Araf, and a former postdoc, Shira Chapman. And please interrupt if you want to ask questions. I imagine that I don't need to encourage you to do so. But in case you need the encouragement, here you have it. So what's this talk all about? So normally, from a low energy effective field theory point of view, we often view gravity as just some low energy effective field theory. It has some cutoff scale lambda UV, and we would normally think that we have no access at all to any information about energies that are above the UV cutoff because it's a low energy effective field theory. However, gravity is also very different in some sense from a standard low energy effective field theory. It's really a peculiar beast. For example, even in low energy effective field theory, you can make black holes. And if you make small black holes, you can make black holes with a high temperature. And we can compute the entropy of the black hole using purely gravitational methods. And from that, we apparently can construct something like a high temperature partition function of the degrees of freedom of the theory, although we are only using gravitational methods. So gravity knows something about the high energy regime of the theory. It apparently knows something about the density of states at high energy. And that's not something you would normally have access to in a standard low energy effective field theory. Another thing you can do, for example, if you think about AGS CFT, is that you can put your boundary on some Euclidean manifold. And very often there is a weakly coupled Boer gravitational solution that has the right asymptotics, and that allows you to compute in some approximation the partition function of the field theory on Euclidean manifolds. That includes things like finite temperature correlations, correlation functions, and that temperature can be pretty high. Doesn't need to necessarily be. And apparently, again, this is the information that's contained in the gravitational theory in the book. And again, it's telling us much more than what normal low energy effective field theory would tell us, because normal low energy effective field theory would not tell you what all these high temperature correlation functions are, etc. And then thirdly, because of all the recent exciting work about islands and replica wormholes and so on, we also know that just using the low energy effective field theory that contains gravity, we can actually recover the page curve for black hole evaporation. That does not mean that we can actually recover in detail the final state of the evaporation, but we can apparently reconstruct roughly the page curve, which, as probably is well known, is simply a curve that tells you how much entropy is contained in the radiation that leaves an evaporating black hole. And if you assume that you can cleanly separate the degrees of freedom in the black hole from the radiation, then it's like separating a quantum system into two pieces. And then because the whole system is in a pure state, we do know that the entropy in the radiation must go up and then eventually must go down again, because by the time the black hole has completely evaporated, and we believe the theory is unitary, etc., there should not be any entropy left.
Sorry, Jan, I'm sorry to ask you this because I'm sure you'll dwell on this, but what you say is quite true, say if you take the last point, but it seems that gravity can calculate only very particular things, right? For example, the detailed S matrix is not something we can hope to compute in some crude, saddle point approximation. But the page curve, as you say, the entanglement entropy comes out roughly right. So it's only very particular quantities, isn't it?
Yeah, it's very particular quantities. And yeah, so one of the key questions I want to ask is, what are those quantities? Mm-hmm. Can we describe the quantities that are computable and distinguish them from the ones that are not? And what kind of information is contained in this low energy effective field theory? Mm-hmm. Because in all these examples, what we're computing is some sort of coarse-grained UV data. We're not computing something really microscopic high energy. We're computing some coarse-grained high energy information. So yeah, that's very correct. So one of the points I want to make is try to be more precise about what you can and cannot compute.
Thank you.
Yeah, thanks. Now, famously, if you have this low energy effective field theory that has gravity in it, it also knows about certain Euclidean wormholes. It's conceivable, it depends a bit on the details of your theory, that you have a solution that looks a bit like in the picture, where we have one asymptotic region, a second asymptotic region, and two more. You can stick some operators, boundaries, and if you look at this cartoon, it apparently is computing for us some sort of weird, disconnected correlation function where you have different field theories. I will very often use ADS-CFT terminology, whereas some of the lessons hopefully will be more broadly applicable, but to say things precisely, we very often have ADS-CFT in mind. So this would then be suggesting that apparently if you just do a gravitational computation, for some weird reason, there is going to be a correlator that involves 4 disconnected field theories that live on different manifolds with 6 operator insertions. But apparently this connected correlator contributes, which is very strange. It spoils factorization of computations in field theories naively. And this is one of the standard puzzles that you get when you consider Euclidean wormholes, and has led to these discussions about baby wormholes and averaging and all that. Now, whether or not you want to include such wormholes or other funny configurations in your low energy effective field theory may depend a little bit on what you mean by low energy effective field theory. But what I mean by that is there's different perspectives on what you could mean by low energy effective field theory. In most of the work that has been done that is related to averaging, etc., people use either JT gravity or a version of that or pure 3D gravity, and treat them as complete theories. So they just try to treat these theories as if they were UV complete theories. And those are clearly highly anomalous, because as soon as you go up to 4 dimensions and you have propagating gravitons, you cannot just take this low energy effective field theory of pure 4D gravity as a complete theory. It doesn't make any sense. Well, I think there are people in other fields that might think it does make sense and you can quantize it as is using various techniques, but in string theory, we tend to believe that that doesn't make any sense. Here, I will always talk really about low energy effective field theory, which means that I will imagine there can be high energy degrees of freedom and that there typically will be high energy degrees of freedom that are invisible in the low energy effective field theory. If you have a low energy effective field theory and it has different saddle point solutions, for example, and if there's an exponential hierarchy between the saddle points, then you can wonder whether the subleading saddle points are even part of your low energy effective field theory. They might be okay solutions of the field equations, but it might not make sense to include such subleading exponentially suppressed things in your computation, because all the things that you integrated out would give larger contributions than the things that you keep. So it's not clear in general that if you have a low energy effective field theory and you have several saddles that you should take them all seriously. Presumably the leading saddle is the one that you should take seriously. And then if there's other sub-leading ones, maybe you should take them seriously, maybe not. It might also depend on details of the UV completion.
So Jan, it might also depend on the precise contour prescription over which
very much so. So there might be, as you know, there's all these issues in Euclidean gravity, you know, with the sign of the conformal factor and the fact that you need to choose the right contour. And so it might also depend on the contour. If you choose the right steepest descent contour, it might miss some of these saddle points, etc. So yes, absolutely.
And it's also, it's conceivable that there is one contour choice that includes them and another contour choice that does not include them. One of them is dual to some average theory, while another one is dual to, you know, genuine field theory.
That's right. And in fact, to determine the right choice of contour might require UV knowledge, right? Yeah, that's right.
Absolutely.
Yeah. You can ask whether correlations function, if you compute a correlator with an exponentially long time scale, whether that's part of your low energy effective field theory. You might think that if you have a very, very, very long time scale, that eventually you're leaving the validity of low energy effective field theory, because you start to be able to resolve exponentially small energy differences. And that's typically not something that you can do in effective field theory. And you can ask whether, you know, sometimes people write down the low energy effective field theory, but still add some non-perturbative things to it, like D-branes, because you can consider D-branes as solitons in your low energy effective field theory, for example. And then it's a question of whether you feel that these are part of your low energy effective field theory or not. And these might all to some extent be choices that you can make. And that without a complete UV description, it's just from a low energy point of view, it's a choice that you can make. It's a bit of a choice also what you mean by if you have a gravitational theory, what you mean by low energy effective field theory. So in this talk, I would like to consider the question, what is the dual quantum mechanical description of a low energy effective field theory that includes gravity? So here the word dual refers to ASCFT, but the lessons that we learn are hopefully more generally applicable. And this notion of dual, as we were saying, depends on what you mean by the low energy effective field theory. It might also depend on this choice of contour, etc. And as I wrote in the last point here, there might be different UV completions of this low energy theory. You could imagine that there is some UV completion which is a single unitary theory. There might be another UV completion which is effectively an ensemble average of theories. And all of this depends on choices that you can make, as we were discussing. But the main question again in this seminar will be, what's the dual quantum mechanical description of a low energy effective field theory that includes gravity? Now, the first piece of information we can consider is the so-called spectral density. Because if we have our theory and we can put a black hole in it, we can apparently, by computing in the low energy effective field theory, in my gravitational theory, I can compute the entropy of a black hole. It's the approximate entropy of a black hole, right? It's the area over 4 times G Newton, maybe plus perturbative corrections. And that allows us to obtain an approximate expression for the partition function. And if we have an approximate expression for the partition function, we can do an inverse Legendre transform and get an approximate expression for the density of states. But if you do this computation, you take your gravitational theory, you compute the entropy of a black hole, you compute the density of states, it's going to give you some smooth function. We will not see the actual microscopic density of states, which is a sum of delta functions. That has been smoothed out by our gravitational computation. To resolve this individual sum of delta functions would require us to, do things with like an x minus s accuracy, and that's simply not something we can do in low energy effective field theory. If one could see this delta function density of states, that would be cool, because that would mean that we would have access to all the individual microstates of the black hole, purely in a low energy effective field theory, which in some sense is the idea of the fuzzball program. but it's hard to see from a statistical mechanics point of view why that should be possible. There might be exceptions, maybe there's some integrable sector of the theory, maybe there's topological theories, or maybe if you have supersymmetry, the situation could be better, especially if you have supersymmetry. Typically the gap is no longer e to the minus s, but if you have DPS states, the gap is typically a half or one or something like that, and that is resolvable in principle in low energy effective field theory.
So, sorry, Jan, can I ask you a question just to make sure I understand your thinking, if I may, which is when you say whether you can understand some features in the low energy effective theory, if I understand you mean in the say the quantum mechanical, say the dual field theory, which is dual to the theory of gravity. Is it in the context of ADS CFT? Do you mean, can I understand some features that I might obtain through semi-classical gravity in a low energy approximation of the CFT? Is that what you mean? Or
no. It's I take a low energy effective field theory approximation to the bulk theory, to the gravitational theory in ADS.
Okay.
But that contains more information than just the low energy sector of the boundary theory. Right. In particular, it knows about the high temperature partition function, for example.
So then you want to know, but then, and what you want to know is, so what was your question? So that's true, what you say is true in the bulk, and you want to know what information of the boundary theory it encodes in a...
Yeah, I want to know what information in the boundary theory is encoded by the low energy effective field theory in the bulk.
Okay.
And that is more than just the low, clearly it includes the low energy, some sort of low energy or low dimension sector of the boundary theory, but it includes more than that.
Right.
And the question is, how much more does it include? Okay. And what's the structure of the things that it includes?
Right. Okay, thanks, yes.
Now you can ask this in the gravitational theory. You can also ask this question that in field theory you would never ask, namely, are there connected contributions to a two-point function of partition functions or spectral density? If you think of microscopic UV, then these connected point functions vanish. But if you average over theories, then these connected two-point functions need not vanish. In low energy effective field theory, if you do have wormhole configurations, like in this cartoon here, that strongly suggests that, that these correlation functions here should not be equal to 0. Because there is some connected gravitational piece. And then you may ask the question, how can this be? How is it possible that we have a low energy effective field theory approximation to a single UV theory, but that predicts somehow a connected two-point function for the partition function? So one way to think about these types of computations is the following cartoon. Just consider a large set of n random phases e to the I phi I. We just take the uniform distribution on the circle and we pick n numbers. Then if you compute, then you know that the average of those phases will be equal to 0. But the absolute value of the sum of those phases will have a non-trivial expectation value. You know, that the sum of those phases, like if you look at this particular expression here, that's something that fluctuates. Sorry, that's something that fluctuates, and its fluctuation will have a certain size. And you can see what the size of the fluctuation in the random phases is by taking the sum of the phases and multiplying it by its complex conjugate. And then what you will see is there's a diagonal piece, which is just n, right? Because the diagonal, you just have e to the I phi times e to the minus I phi, that all adds up to 1 and to n. And then there's a whole bunch of diagonal pieces that are erratic. Now the proposed picture is that this diagonal piece, this resonant piece, is visible in the low energy effective field theory. But the off-diagonal piece, which is erratic and fluctuates a lot, is invisible in gravity. So in other words, the proposal is that the low energy effect, this is just at a cartoon level, but I think this captures the essential idea. The low energy effective field theory is sensitive to the average size of fluctuations. It measures like a variance, but it's not sensitive to the actual individual fluctuations themselves. So this is like an important statement here, or proposal, if you wish, is that this is precisely what is going on. And now you could ask the question, what happens in the UV theory? Well, in the UV theory, there are different possibilities. If we agree that this term is always visible in the low energy effective field theory is equal to n, then in the UV theory, there's several possibilities. One possibility is that the relevant gravitational solution that I was talking about, this wormhole solution, is unstable or no longer a leading saddle point. It somehow gets destabilized. It simply is no longer part of the right prescription of your UV path integral, and therefore it no longer exists. And then factorization is restored. You could say that this wormhole configuration might remain as an off-shell configuration. That does not mean that it needs to contribute to this computation. So that's one logical possibility. A second logical possibility is that all the UV physics, all the high energy stuff, it adds all those fluctuating things back in. And if you add those fluctuating things back in that are only accessible using the UV physics, then factorization is restored, because now you simply add that to your leading term n, and then the whole thing factorizes again. And a third possibility is that perhaps your UV theory is an average of theories. And if you do an actual average of UV theories, then it could happen that, that this thing is simply averaged away to zero. And then factorization is not restored, but there was no reason for factorization to happen anyway, because the theory was averaged. So that's a crude picture of how one can think about these wormhole solutions. And as you see, there's in principle different choices on what happens in the UV, and it could either be a single theory or it could be an average theory. You could say that the low energy effective field theory is a bit agnostic about it. It just depends on the additional details that come in as you UV complete the theory. Yeah, maybe. You know, and famously these kind of wormhole configurations were used to study JT gravity. And one of the nice things that one found, although I think this is with the logic that I'm presenting, this is outside, strictly speaking, outside the scope of low energy effective field theory, is that those wormholes seem to be able to detect things like eigenvalue repulsion in the spectrum. Now, I'm not entirely sure whether we should view that as a property of low energy effective field theory or not, because in order to get it picture, we need to sum a whole bunch of exponentially subleading saddle points. And as I was saying before, it's not entirely clear to me whether in low energy effective field theory, we should in fact be allowed to do that, because perturbative corrections to the leading saddle point might be much larger than all the things that you add to the subleading saddle points. If you treat JT gravity as a complete theory, then of course it's fine, right? And we think we have complete control, and then you compute whatever you want to compute. But if you view JT gravity as a low energy effective field theory, then it's not clear to me that we would always run into this behavior, and that it's even part of the prescription. But anyway, here we see another interesting universal feature, this slope ramp plateau behavior, which has to do with the fact that the spectrum has eigenvalue repulsion. But this will not come back in the remainder of the talk.
Jan, one question.
Yep.
So when you say, if you think of JT gravity as a complete theory, then of course we can do it. But a priori, should we not be able to say whether it is UV complete or not, whether it's a I mean, whether additional degrees of freedom are required in the UV, or this gravity by itself is giving fine answers? Because otherwise, what is the test a priori?
Well, this is a highly atypical low-dimensional example, because in higher dimensions, because the theory is not renormalizable, it's not UV complete as it stands, right?
Yeah.
And 2 and 3 dimensions are special, and this theory does not have propagating graviton degrees of freedom, so it has a chance of being UV complete by itself. But I think that's very atypical. I think only with some low-dimensional examples, there is a hope that maybe it makes sense to view these theories as a standalone theory. But even in
atypicality of JT gravity could be a big factor in this entire discussion, right? I mean,
that could be the case.
Yeah.
So, for example, if you might think that pure 3-dimensional gravity is a perfectly fine theory because it's topological, and therefore that it should be perfectly fine and make sense. If, however, in that case, you try to interpret the theory in terms of a dual field theory, and you do the sort of naive computation that you think spits out the boundary partition function, the one that Maloney and Witten did, then you find a spectral density which is not positive definite.
No.
That tells you that you either need to add more ingredients to the theory or do something else to the theory, but as it stands, that computation gives an ill-defined answer, and clearly you need more ingredients to have a well-defined theory. So there can be simple diagnostics, even in these low-dimensional examples, that somehow you're missing fundamental aspects of the theory. And you haven't understood precisely. In JT gravity, I'm not sure there is any such problem.
The question of whether the theory of gravity is UV complete or not, isn't it a priori independent from the question of whether the dual theory has a nice spectrum and so on? Shouldn't the first question, doesn't the first question only mean whether you can do the gravity path integral in a finite way or not, right? How?
Well,
because we are going back and forth between these descriptions, right? So
yeah, maybe. Well, depends on the type of question that you want to ask and what types of computations you think should be doable and accessible in a UV complete description of a gravitational theory.
Okay.
If you just want to compute partition functions and you are happy to find a partition function and you don't care whether or not it admits a microscopic interpretation as the trace over a Hilbert space, you're happy that it computes well-defined numbers. If you're happy with that, then you could say that 3D gravity is a fine theory. You can compute numbers; they're finite.
Okay.
But that's not what we normally mean by quantum gravity, right? We mean a theory which we've quantized. I mean, a traditionalist, at least, or somebody 3 years ago would have said you need a Hilbert space, not an average over Hilbert spaces. Right? So already JT gravity fails that criterion.
Okay.
That's right. Yeah, so that's right. However, if you say, can I meaningfully compute partition functions? Yeah. Can I associate some numbers to the partition function? And I don't care whether it looks like the trace over a Hilbert space or anything like that. And in JT graphs, you can compute those numbers.
You can, but I thought the idea of quantum gravity was that you get a unification of gravity and quantum mechanics. And quantum mechanics includes Hilbert spaces and unitarity and so on.
No, yes, that's right.
Okay, thanks.
No, but can I just say one thing? I mean, just to go back to what Jan was saying. Okay, even if we take it as a path integral definition, JT gravity can be by itself a UV complete theory, and yet at the same time might be a low energy effective theory for another UV completion. Example being, JT gravity arises as the near horizon limit of a BTZ black hole, say in ADS3 or higher dimensional examples. In those cases, say in ADS3, the partition function admits and description in terms of integer density of states, which the JT approximation doesn't. And so, it's clearly two different answers depending on what you add in the ultraviolet. But JT by itself, at least using the prescription everyone is adopting now for the contours, does give, as Jan was saying, a perfectly well-defined answer to the path integral, at least. So just even leaving aside the Hilbert space question, I mean, I think something can be a perfectly good ultraviolet complete theory in the sense of giving us good answers as the answers to path integrals, but at the same time might also appear as a low energy effective theory with additional stuff where that ultraviolet stuff adds on to give a different final answer. You know, sorry, I just thought I would say that.
Yeah. So yeah, maybe I think I agree pretty much with every. I mean, historically, I think what Shiraz was saying, like, what's the theory of quantum gravity? Well, it's a theory that is quantum mechanics, that has gravity in it, and has well-defined Hilbert space. that's the thing that I guess historically in string theory you would be looking for, right? Yeah, no, but yeah, I agree with all your comments. Yeah. But anyway,
it could be, sorry, you must go on, but I mean, it could well be, right, that some UV complete theories of gravity don't admit a Hilbert space interpretation, but admit an interpretation as some kind of an average. That could be, right? And yet others could admit an interpretation in terms of a standard Hilbert space and quantum mechanics on it. I mean, we don't have to.
If you think, yeah, if you feel that an average over theories is an acceptable answer to the question that you were asking to begin with, then yes. But maybe this is not what we thought for a long time in string theory to be an acceptable answer to the question. Yeah. So what can be like some sort of formalism to capture some of the features that we're seeing? So here's a sketch of some formalism. Suppose that what we do when we go to compute the low energy effective field theory of gravity is that it's described through some coarse graining procedure in terms of not a single low energy effective field theory density matrix, but there is some measure on the space of density matrices. So this measure will be, if you just restrict to low energy matrix elements, this measure will simply be 1 or 0. It will just agree precisely with the low energy effective field theory. But it will be coarse-grained at the level of high energy states. So there will be some measure. And that measure could arise, as in this example, by doing an actual average over finite temperature theories with a bunch of random coupling constants J. That could be an example. But it could also simply be a standard coarse-graining type of thing, or a block spin, renormalization group step, or something that implements some sort of coarse-graining. So you could imagine that there exists some measure that arises either way. Again, we can be agnostic about whether it arose through coarse graining a single theory or through averaging, but some measure arises. And that's part of my low energy effective field theory description. Now, can such a measure capture these wormhole-like features, for example? And the answer is yes. And it happens typically if the measure has the property. So here is just the average of the density matrix. But with the same measure, you can also compute the average of rho tensor rho. And there's a priori no reason that the average of rho tensor rho should be the same as the tensor product of the average of rho. The difference of the two is essentially the variance in the measure, and typically the variance is non-zero. And if you make a very simple ansatz, which you can make completely self-consistent for what this average of rho tensor rho could be, it could, for example, have the structure of A tensor A, where A is some density matrix, plus S times B tensor B, where S is the swap operator that flips the two copies of the Hilbert space, and B is yet another density matrix. And this second term here, this one could be much smaller than the first one, but you could imagine that's there. It's easy to write down some measure that spits out this type of behavior. And if you would have this structure and you would compute this product of one-point functions, and you compute the average with this measure on the space of density matrices, Then you find from the first term, this A tensor A term, just two disconnected pieces, two disconnected one-point functions. But from the second one finds a single connected two-point function. And this is like, again, a cartoon version of this wormhole picture. It's not literally what we have in mind for the wormhole, but it's a mini version of it. So here we see that when you actually have this average of density matrices and you compute just the product of two one-point functions, which must factorize in the full microscopic theory, that because of the coarse graining that you do, or averaging over series, you can get a structure where you get like two actual disconnected one-point functions, but also a little small connected piece. It could be much smaller, it could be exponentially suppressed, but it can simply be there because of this structure.
So, sorry, Jan, I'm sorry to slow you down, but what is the swap operator doing? Without it, you wouldn't get trace BO1, BO2, is it?
No. So S is simply the thing that if you have two states, there's two copies of the Hilbert space because we have two density matrices. It's simply the thing that flips the two things.
And you need that, huh, for this trace O.
Yeah, because then
Okay.
you can maybe see roughly why that spits out a single trace, right? Because you apply.
Oh, I see.
It glues the indices together in the right way. Yeah.
Right. Okay, thank you. I got it.
So this is an example of a structure that this would be. So one thing that, for example, you can propose is that if you find some, if you have some low energy effective field theory of gravity, and it has things like wormholes and other funny solutions, and it has this kind of structure that arises due to some wormhole-like configuration or something else, then a simple explanation for the emergence of this structure could be that you have this particular distribution on the space of density matrices. And it could well arise from just a silly coarse graining of your UV variables. This is connected a little bit to some other work that in some sense this is very close to, although it's written in a different format, to some work that the UBC group did last year, where they showed that similar structures arise if you do unitary averages over high energy states. If you do unitary averages over high energy states, it turns out you do get a structure that that's written here, including this kind of swap structure. Because if you do an integral of the unitary group of two unitary elements, it does you automatically give two delta functions, but there's also the cross term that you get. So there is a very natural way to get this kind of structure from unitary matrix integrals. So from a vanilla coarse graining. It was a nice paper by Hong Liu and Vardan, where they show more generally, using some Keldy-Schwinger story, that this permutation structure, they argue that it is the thing that actually sort of dominates many computations. So if you have more than two density matrices, you can have other, not just a swap operator, but you could have arbitrary elements of the permutation group that permute the copies of the Hilbert space. And that those, they argue but don't prove in certain regimes actually dominate the computations. It's also a structure that Altlaat and Sonner found, again, in a different way in trying to develop some sort of universal symmetry breaking approach to these types of problems, using a sigma model for the goldstones that control the universal sort of replica symmetry breaking structure. And also in a recent paper by Janssen, Mirbabati, and Zograf, they were asking a bit of a funny related question, namely, suppose that you have a measure like this and you compute the moments of the stress tensor. There must be some inequalities between the moments of the stress tensor that hold in order for this to come from a positive definite measure. It's an old problem in mathematical statistics, that if I give you a probability distribution and I compute the moments of all the variables, to give a complete list of inequalities between all the moments that guarantee that it came from a well-defined measure. The lowest order inequality is that the variance should be non-negative. But similarly, there are higher order inequalities, and I think that's still an active field of research to figure out what they are. It's the so-called Stieltjes problem, which dates back to the late 19th century. And you could, in principle, in the gravitational setting, if you have access to all these moments, you could test whether it came from a positive definite measure or not. And in this last paper, I think they looked at some models and found that in some cases these inequalities are violated, so that those low energy effective field theories clearly cannot come from a bona fide UV theory. But you can ask, what are the principles? What is the general structure? Can these types of structures that I'm describing here, with like a measure on the space of density matrices with this permutation structure, is that a natural thing to arise, for example, if you do some notion of RG? And is this structure sufficient to capture all the features that we see in low energy effective field theory? Those are some open questions. So now I'll move on to something else, where I will no longer be speaking about density matrices and averages over states, but I will now start to look at correlation functions, where some different statistical things appear. And then at the end, I will ask the question how you combine these two perspectives, one which is more like an operator point of view, and the other one which is more like a state point of view, whether these can all be put together in one way or not. And that's one of the open questions at the end. Let's see. But a priori, so one of the other things that this low energy effective field theory computes is finite temperature correlation functions of operators. And it might not be obvious a priori how those can be computed using state averages only. So in order to capture those properties of the low energy effective field theory, what we're going to do is we are going to take all these operators whose correlators we're studying, and we're going to replace their high energy matrix elements by statistical quantities. So again, it will all be statistics, but now for operators rather than for density matrices. And the simplest example of this way of thinking is the celebrated eigenstate thermalization hypothesis, which is conjectured to hold in chaotic systems. And the statement is that the 3-point function, if you want, or the expectation value or the matrix element of a simple operator O between two high energy eigenstates has two pieces. It has a diagonal piece and it has an off-diagonal piece. There's an exponential hierarchy between the two. The diagonal piece has a simple function f in it, which is a smoothly varying function of the energy, average energy. And the off-diagonal piece also has a smoothly varying function in it. But importantly, it has this RAIJ here, which is a Gaussian random variable in ETH, which means it has a vanishing 1-point function and it has a very simple 2-point function. So it's a statistical, you treat it as if it's, of course, in an actual microscopic theory, this is not a random variable, it is some very specific set of numbers. But ETH says that for practical purposes, you can treat those numbers as being random. And the only thing that we care about is these properties of these random numbers. And if we simply impose these two properties on R, that is sufficient to reproduce the finite temperature 1-point function of OA, but also the finite temperature 2-point function of OA. In some sense, this function f encodes the information of the finite temperature 1-point function of O, and this function g contains the information about the finite temperature 2-point function of O. So ETH is an example where we replace matrix elements of operators by statistical quantities.
And then, sorry, Jan, I don't know this so well. And then the idea is that the higher endpoint correlators are not so important, or you can similarly add additional stuff? What's that?
Yeah. To get, that's a great question. To get the higher correlation functions, you need higher moments of this random variable. So it's not purely Gaussian anymore.
Okay.
This random variable also needs a third order moment in its probability distribution and a fourth order moment in its probability distribution.
Okay.
But the hierarchy between all these moments, they will all be exponentially suppressed if you express it in terms of R.
I see. Okay.
So there is some exponential hierarchy that tells you that in some sense the leading piece is Gaussian.
Okay. Thank you.
But these subleading moments are important to get these other correlation functions out. So they are part of the low energy effective field theory discussion because they compute standard, say 4-point finite temperature correlation functions, and we can compute those using the gravitational theory. We just take say Euclidean black hole background and stick in some operators on the boundary and just do the usual ADS-CFT computation. So a simple cartoon that you can draw is here. So we split the spectrum in low energy or light operator states and high energy or heavy operators and states. These ones will typically have labels A, B, C, and so on, and these one I and J and K, etc. And then you can draw a simple sort of cartoon for ETH. I'm not going to, this can just be ignored for most of what they say. But what's interesting is that you have this 3-point vertex here. You have this 3-point vertex here, which is a vertex between 2 heavy lines and 1 light line. And it carries a random matrix with some amplitude. And if you think about it a bit more, it turns out that if you now take an ADS-CFT point of view, that this 3-point vertex, it's an OPE coefficient between 1 light and 2 heavy operators. Because we're just computing this matrix element in the CFT, it's just a 3-point function, and a 3-point function in the CFT is just a coefficient in the operator product expansion. So another way to think about this is that this is representing some OPE coefficients, and that we are apparently treating the OPE coefficient as a random variable. Now, if you think about it a bit more, you can draw all kinds of diagrams in a CFT that contains light fields and heavy fields. And if you think a bit more about it, it turns out that all diagrams that you can draw that have light operators on the external legs and heavy operators in internal propagators and loops, that all these diagrams, although they involve all these heavy operators, that all these diagrams are computable in ADS-CFT, typically using only the low energy effective field theory of ADS gravity. This top left diagram, it's a finite temperature 2-point function. The diagram below it, this one here, this corresponds to, for example, a genus 2 computation in a 2D CFT. This would be a genus 3 computation. There's 3 loops. This is a finite temperature 4-point function. This is a 3-level 6-point function, sometimes called, I think, the snowflake channel or diagram or whatever. And this is another channel that computes a 2-point function at finite temperature, etc. So these are all.
Yeah. Sorry, Jan, quick question. The fact that you had that e to the power minus SE by 2, that gets cancelled against the measure factor so that the low energy correlators are finite, right?
That's right. Yeah.
Okay, thank you.
That's correct. Yeah.
And this is the same logic then you could use to deduce the SE scaling of the higher point correlators.
For that particular case, yes, but in general, it's not so easy to estimate the right E minus S prescription, because you don't just have a density of states in an actual correlator. There's also conformal blocks that multiply the whole thing, and those conformal blocks might give further dependence on the density of states. So what you say is correct for finite temperature endpoint functions, But for these, say, higher genus correlators or even this tree-level diagram, this intuition is less clear.
Thank you.
So since these are all accessible.
Sorry to interrupt you. Just to ask you, I mean, usually the words I would at least say, but I want to ask you is, oh, well, you know, the heavy stuff has gone into the black hole background in which you are computing then the correlators of the light stuff. And so gravity is clever enough to incorporate that. And I want to ask you whether you think, of course, you might probably say that, I'm not sure, but is it because gravity in a sense arises as a low energy approximation in some kind of large end limit always that we can get away like this? Okay, you don't have to answer that, but I just have always had this vague thought. So okay.
Well, there might be something like that. Yeah, I can't say something terribly sharp, but I recognize your sentiment and I sympathize with it, but I can't make it very precise.
Okay. Thank you. Sorry.
No problem. Yeah. So since all these diagrams are apparently computable, are part of what all these diagrams in the CFT are part of the sector that is dual to low energy gravity. Mm-hmm. So whatever the dual description of our gravitational theory is, it should include all these diagrams. Mm-hmm. However, individual heavy lines and operators and even the detailed spectrum of high energy states we do not know. So we need some formalism that captures all these diagrams and all these computations without capturing detailed high energy physics. And basically the proposal, is the so-called OPE randomness hypothesis, is that all these vertices should be replaced by random variables. So we should reinterpret them all as moments of a probability distribution. So all these OPE coefficients is the proposal that appear either with 3 heavy indices, with 2 heavy and 1 light, or with 1 heavy and 2 light indices. We're going to claim that these are all random variables in terms of these heavy indices with an approximate Gaussian distribution, but also with higher moments in general.
So 2 heavy and 1 light is what you explained to us was ETH, right?
Yeah.
So it's a generalization to more general distributions.
Yeah, as soon as there is at least 1 heavy index, there will be a statistical aspect to this quantity because the individual heavy index is not resolvable. And so the claim is that what the gravitational theory has access to is moments of these probability distributions. But those moments become harder and harder to compute as they become larger. And you don't have enough access to the moments to, not enough detailed access to the moments. You can only compute them in some 1/n expansion. It's a gravitational theory. So you can compute the moments of these probability distributions up to some order. But those moments are not sufficient to reconstruct their individual values. That is beyond the gravitational approximation. But the moments of these probability distributions, that's the thing that gravity sees. And that's essentially the claim of what the dual is of gravity.
Sorry, in particular, in the first example, the ETH example, it's the moments of this Rij that you can.
Yeah, that's right. Yeah.
Thank you.
Yeah. But if you compute the first 23 moments of Rij, that's not sufficient to reconstruct their microscopic values, which are precise erratic numbers, right? That's not part of the low energy theory, right, but their moments are.
So you can only compute you can compute the number. If the number of moments you can compute is p, you can compute p at n, in the limit n goes to infinity. So p is fixed, n goes to infinity, and so then that's not enough.
Yeah, you froze for a second, but I guess it's true that you cannot compute this moment up to infinite order. No.
And up to order n, presumably, or e to the
power.
Yeah.
Typically, you have in mind that as long as if the number of if you compute, and it's the same as computing endpoint correlators, is typically no longer part of the low energy theory. Yeah, correct. Yeah, that's the intuition. So that's basically if you want to translate your gravitational information into the CFT, that seems to be the information that we get. So we know you can analyze these statistical properties from many points of view. Let me not go into detail here, except that maybe in 2 dimensions, we do know various asymptotic formulas that were developed by Collier, Maloney, Maxfield, and Ciares in 2019. So there's all kinds of asymptotic formulas, at least for the second moment, that are available. And you will recognize in all of these, there's all kinds of exponential suppression factors here that are roughly like a Cardy-like suppression factors, like e to the minus s or e to the minus s over 2, etc. Yeah, I have 2 more points to make and then I'll wrap up. I'm going to ask exactly how much time I have because that will depend on how fast I will go through it.
We are flexible with time, so please go ahead and.
Okay, well, I don't need that much more time, but just to be nice to finish. Okay, so here's the first example of this thinking. That's the following peculiar example. It's the square of the genus 2 partition function in a 2D CFT. And you might wonder why one takes such a ridiculous example to compute. But that's because if you have 2 genus 2 Riemann surfaces, there's an extremely simple wormhole that connects them that exists in the classical theory. You don't need to include quantum corrections or anything. It just is a classical solution that was discussed in detail by Maas and Maldacena already in 2004. And that's the simplest possible 2-sided ADS-CFT solution that doesn't require any weird ingredients or bells and whistles. It exists in pure 3D gravity at the classical level, etc., etc. But let's take this logic. So I was saying that what does the gravitational theory produce? It produces moments of these distributions. Okay, so let's take that proposal now. So now we assume that our OPE coefficients, in particular the ones that stand here, that these are proper things with a Gaussian random distribution plus higher moments. Let's now look at
these are heavy. All
this is all heavy. Yeah. I'm going to look at a special regime where everything is heavy. There's no external light line. It's a 0-point function, so all the loops can be heavy, right? I'm going to be stated differently. I'm going to be in the regime of moduli space where it's dominated by heavy. And that regime in the moduli space is depicted in the cartoon below. So you can think of a genus 2 Riemann surface as 2 spheres connected by 3 propagators. And you know, the modulus of the propagator is like a temperature. And you just need to make sure that those 3 propagators are high temperature propagators. And then you're in the regime in moduli space where you want to be. So I assume here that beta is small. And then, as you can see in this cartoon depiction of a genus 2 Riemann surface, you have states running into 3 propagators. And it's basically a 3-point function on the left 2-sphere, 3 propagators, and then a 3-point function on the right 2-sphere. And they all combine together in a single, single expression that looks like that. Right? The E minus 3 beta delta is from the 3 propagators, and then C and C star are the OPE coefficients. So the square of the genus 2 partition function is just these 2 terms in brackets. Now, if you take seriously the statement that these C's are random variables, and you use that to try to compute this product of the genus 2 partition functions,
Jan,
there is one
question. So why can't there be other insertions in the propagator, light insertions or something? Because there could be off-diagonal terms also, right? Delta I can go to delta I prime, can't it?
Well, in this picture of the genus 2 partition function, you literally glue cylinders where you basically the propagator is q to the L0 times q bar to the L0 bar for a cylinder. So that's diagonal in primaries.
No, but you can imagine, inserting a 3-punctured sphere in the middle of the propagator. which is a non-zero sphere. Namely, one comes delta I, the other on one end comes delta I, the other end comes delta J, and the third end is some other operator. I mean, that could also contribute to this sum, right? A priori. I mean, why is this diagonal gluing?
Well, this is the right description in a particular limit of the moduli space. You can, I mean, if you draw this as a Feynman diagram, it's this type of diagram. You could, in principle, also go to a different corner of the moduli space where it looks more like this diagram. That's a different discussion. But if we decompose the higher genus Riemann surfaces and we do a Pan's decomposition and so on, then this is the correct picture in this corner of moduli space for a genus 2 Riemann surface. There might be other possibilities, but typically they will be relevant in other corners of moduli space.
Okay.
So this is supposed to be a description in one particular corner of moduli space only.
Yeah, but even in that corner of modular space, I don't understand why can't you, in your first diagram, for example, why can't you just put another vertex there in the propagator?
You mean here?
Yes. Yes.
And where would this go?
Yeah, just the insertion of some. Okay, that would be. I mean, you can. Yeah. Okay.
This would be a 1-point function. Now I would have to put a light operator. So this would compute a 1-point function. And if I connect it somewhere else, then I'm doing a genus 3 computation and not a genus 2 computation.
Okay, fine, thank
you. Right. Yeah, so with this representation, we can now compute this product of these two genus 2 partition functions. So there's the first, these are Gaussian variables. So there's the first contraction that you can do, and you can just do the computation and put in the asymptotics of the coefficients and all that. And if you do that, you do correctly reproduce the square of the genus 2 partition function. You can, however, also, they're Gaussian variables, so there's also another Wick contraction that is there. And then there could be, in principle, 4th order contractions from the higher moments. But just let's first look at the leading Gaussian approximation. That gives this contraction pattern. And we can also do this. This is still purely a CFT computation. However, assuming that the C's are Gaussian random variables. And this gives another result, which is the unity if you plug in all the numbers. So there are two possibilities here at the Gaussian level. One is an exponentially large contribution coming from this disconnected piece. And then there is a finite, so it's exponentially subleading contribution that comes from this other Wick contraction. And then there could, in principle, be other higher order moments that are relevant, say the 4th order moment of the C's, but I'm ignoring that in this computation. The idea is that the 4th order moment will be further exponentially subleading compared to this one. And that is something that one needs to prove. That requires some genus 3 computation that we're doing right now, which is a bit annoying, but it seems to be true. So, and this is the same thing that this structure agrees precisely with what you get indeed in the low energy gravitational theory. Because in the low energy gravitational theory, there is a disconnected solution, there is a connected solution, and the hierarchy between the two solutions is also exponential. And the exponential suppression factor is the same as what I got from my previous computation. You can just compute, this is a gravitational computation, you can try to compute all these things, I'm skipping those details, but you do get the same exponential suppression factor. So this shows you that if you postulate that these OPE coefficients are statistical in nature, as far as gravity is concerned, and you follow that logic, then you find from the CFT a prediction that there should be a connected contribution. Then you go to the gravitational theory, where you indeed see that connected contribution is this Maldacena-Maas wormhole, and the exponential hierarchy between the two agrees. It would be nice to also check the order 1 coefficients or maybe even moduli dependence, but that seems excessively technically complicated, so we haven't been able to do that. But at least it's at this level, this discussion shows that this Gaussian assumption is consistent with the gravitational computation and includes even this interesting little wormhole configuration.
Jan, the standard eigenstate thermalization hypothesis, can that also be thought of as being motivated from this point of view?
Yeah, it's literally that. So the eigenstate thermalization hypothesis, you could say that is simply the statement that the light heavy OPE coefficient is Gaussian with some suitable weight. And that is ETH essentially. There's a nice generalization of ETH that has more than 2 operators in it, and that simply is saying something about the higher moments of the distribution. But it's precisely, literally in the spirit of what I'm saying here.
So one can think of this as a factorization problem for 2-point function, thermal 2-point functions or something like that.
Well, the ETH does not immediately lead to a factorization problem. But you can, well, yeah, it's a nice remark. So in fact, if you take ETH and you again follow the Gaussian logic, you would find that if you take the product of 2 finite temperature 2-point functions, that there would also be like a connected piece.
Right,
From by the same Wick contraction logic. And if you write down, if you add matter fields, for example, I did that computation once for ADS3 just to see how, if you add matter fields, there is precisely at 4th order, and not at 2nd order, but if you have 2 operators on one side and 2 operators on the other side, they can precisely generate enough back reaction to open up a wormhole. So that again, it's a bit harder to put the numbers in that. I never pushed it very hard, but that seems to be perfectly consistent again with this Gaussian proposal.
Yes, thank you.
Sorry, Jan, I should know this, but Maldacena Mouse's calculation was pure ADS3, is it? Or was there more to it in the bulk?
No, this thing, this wormhole exists literally in ADS3. It's literally the solution that's written here.
Yeah.
These solutions always exist as long as this surface has constant negative curvature. This is a solution of the ADS field equations.
True.
However, in higher dimensions, field theories on negative scalar curvature manifolds are unstable because of the coupling to the scalar fields. But in 2 dimensions, that's not an issue. That's why this one in 2 dimensions is nice.
Right.
Now, they have another discussion where they show that, if you have also D-branes, that this thing might be unstable against the formation of D-branes and all that. But I'm not including D-branes in my low energy effective field theory, so I'm fine with this solution.
Okay, thank you.
Jan, sorry, how did your heavy 3-point function scale with entropy?
Yeah, so
okay, and this ratio that you got between the connected and the disconnected, is it essentially from this factor? Does it come from this factor?
Yeah, it essentially comes from this factor, I think, if you go through all the details. Yeah.
Okay. The variance of these CIJKs, they cancel out in the ratio. The ratio between the wormhole and the product of 2 genus G.
Yeah, so a different way to see this exponential hierarchy is that if you do this contraction here, there's now all the indices get connected together. So there's fewer indices to sum over. So it's maybe more the exponential hierarchy is maybe more coming from fewer densities of states being involved than it's a combination of this exponential factor. But that's the same in both computations. However, in one computation here, there's fewer indices in the loop.
Right. So
here you only,
the factor is engineered so as to cancel this factor for the genus 2 squared, right? And
that's
then
right,
it does not cancel part of it in the other one, right?
That's right, because here there's fewer, so it does not cancel, and then there's exponential hierarchy. That's right.
Correct. I see. So this is a very easy thing to compute. I mean, it's a very universal kind of thing. And
this is universal. If you try to push this to a somewhat more complicated computation, then there might be something universal there as well, but it's not so straightforward to find. That has to do with, at some point, also these conformal blocks that are relevant for these higher genus surfaces are becoming important, and those are much harder to control.
And I was wondering whether, from the gravitational point of view, there was some simple intuition to see you would get the same factor. That, you know, the entropy of one is, I don't know, something like that.
Just the genus, right? I mean, you have two disconnected diagrams versus one, right? Shouldn't that give it to us somehow? I don't know. Is there topological some counting factor for the two disconnected guys versus
this in some sense if you compute the partition function for the connected guy, that's a very easy computation. It's the disconnected one that's more complicated to compute. But I don't have an immediate intuition, like the fact that the connected one gives something. If you know that the disconnected one agrees, you can easily see that the connected one gives something of the unity on the gravitational side, because basically the on-shell effective action of this thing is almost zero, just by staring at the actual solution. And if you cancel if you include the usual counter terms, then there's almost nothing left, because it's really very simple. You just need to integrate the cost from one to the other. There's almost nothing there to do. But a good intuition, I don't have. It would be nice to have a more direct link somehow. You might even imagine that if you understand better how to do like a Pans decomposition of a graph of an ADS3 type computation, maybe there's a much more direct mapping between moduli spaces and integrals and so on. But uniformization in 3 dimensions is not exactly the same as in 2 dimensions. So I'm not sure. That's a good question.
So it's not, I mean, in JT gravity, the two disconnected disks went out over the single double trumpet just from topology, right? Just the counting of the genus and so on. It's nothing so simple here, is it?
Not that I'm aware of or have seen. No.
And sorry, just understand. So this answer depends on the moduli of your genus 2 surface, right? The answer.
That's ratio. Right. Yeah.
So could you show your ratio again, please? The ratio between the connected and disconnected. Where is the module?
Oh, we took a very simple thing where we basically look at a one parameter family of surfaces only, which is the one where you have these 3 propagators that have exactly the same temperature and 0 twist. So in principle, there's you could say each cylinder has 1 complex modulus. There's 3 complex moduli, and that together that's the 3 complex dimensional moduli space of genus 2 surfaces. By restricting their temperatures to be real and equal, we basically have a 1-dimensional real sublocus. And there's only 1 parameter in this corner of moduli space, which is beta.
I see. But you could in principle check with the whole genus 2 moduli space, right? Whether this match continues to hold.
Yeah. If you're like, if you have enough muscle and stamina and patience and so on, and you like that kind of stuff, yeah, you could in principle do it. There's no in principle, but like in ADS CFT, I don't think anyone ever managed to compute so the handle body partition function that fills up a genus 2 for all these values of the moduli. The gravitational computation is not available. That would require also a lot of work.
So you could quite easily make a prediction for it from if your proposal is correct.
Yeah, in principle, for the hierarchy, you can. Well, the statistics. Well, it's a longer story, but in principle, yes, yeah. But it's, I mean, it gets pretty damn tedious at some point.
I mean, even your calculation, even the Feynman diagram calculation gets tedious.
Now, this one is not so bad, but if you want to go to different moduli, you first have to estimate the asymptotics of these heavy OPE coefficients. And this, the known result here, which is this one here, this one is only valid when the 3 operators have approximately equal conformal dimensions.
Okay.
If they have different conformal dimensions, you can also do the computation, but it gets much more complicated because now you need to look in detail at the so-called crossing kernels in 2 dimensions that you need to sort of get these asymptotic expressions. And these crossing kernels are integrals of products of many, modified gamma functions. And it's a rather unpleasant exercise to get some actual numbers out. But yeah, in principle,
I suppose I'm asking, there's no sense in which you see geometry coming out of this calculation.
Not directly, no.
Okay.
There might be somewhere, but yeah, it's not clear. Yeah.
Thank you.
Jan, can you tell me? Sorry, just small question. This delta. So in this calculation, you had a high energy operator of dimension delta, but that dropped out right at the end. And
yeah, because that delta, basically the delta, the saddle point value of delta is fixed by the choice of beta, right? It's you either beta really controls the computation.
Okay. Yeah, thanks.
Right. Well, maybe let me very quickly mention this and then I'll wrap up. So another little exercise you can do. That's just a cute little exercise in the spirit of the statement that gravity is computing fluctuations. Suppose we have the same silly wormhole, but suppose that we imagine that we have a gravitational theory that has a global symmetry. Suppose there exists a gravitational theory that has a global symmetry. I'm ignoring the fact that we know that there's a problem with that, but just let's imagine that we have that, right?
Okay.
The low energy effective field theory could have a global symmetry. That might, right? It could have. But if the full, if the gravitational theory has a global symmetry, then this particular computation in this picture, where we have a charged operator on one side and another operator on the other side with the opposite charge, if you just have a global symmetry in the bulk, then this 2-point function would not vanish. There's no reason for it to vanish. You have an operator with charge plus q, one with minus q. There's a global symmetry. There's just some propagator. It's fine. If, however, you do have a gravitational theory that has a global symmetry all the way in the UV, it will be dual to a CFT that also has a global symmetry. But in a CFT with a global symmetry, these 1-point functions are identically 0. There's no charged 1-point function. Also, these charged 1-point functions do not fluctuate. They're identically 0. And what this computation is computing for us is the fluctuations in those 1-point functions, right? Gravity is computing fluctuations and variances of quantities. So there is clearly a mismatch here between the existence of a global symmetry in the boundary CFT and the non-trivial fluctuation that's predicted by the gravitational theory. There's a contradiction here, if you believe that the gravitational theory has an exact global symmetry. And there are 2 ways out. Somehow we forgot that this global symmetry in gravity is actually gauged, which we know should happen, right? And if you gauge the global symmetry, this 2-point function is suddenly 0. And the contradiction goes. There's perfect agreement. And the second possibility is that the global symmetry must be weakly broken, because if you break it a little bit, now the 1-point function in the CFT no longer needs to vanish exactly and it can fluctuate. And because we know roughly what this 2-point function is, we can predict the fluctuation in the 1-point function just from the wormhole, and that gives us a lower bound on the scale of global symmetry break. Just from this low energy computation, just from this wormhole. This is probably an overkill, but it does seem to suggest that it's a nice little, if you just follow the logic, the prediction is that if it's weakly broken in the UV, the scale is at least e to the minus s, because this wormhole predicts fluctuations of that magnitude. So this is, I think, in satisfying agreement with what we know about global symmetries in gravity. Whether there is a swampland type argument for this breaking scale. I'm not sure whether there's one that's much higher than this, or whether the swampland would agree with this. This is, of course, a very small, very high scale of breaking. But I don't know if there's a sharper bound based on general arguments that one can make. It's an interesting question.
Sorry, Jan, I'll embarrass myself. I didn't understand what you said about if the symmetry was gauged, then the bulk 2-point function was 0. Could you explain that, please?
Right. Yeah, that's actually a somewhat confusing computation. Although everyone would immediately, like if you look at most papers that mumble this, it's the Gauss law and it vanishes. Yeah, you cannot have flux through a compact surface.
Right. That's what I thought you would say. Okay.
But if you think about it a bit more, it's true, but the argument might be a bit more subtle. So if you do the bulk path integral, if you do the bulk path integral over all gauge fields in the bulk, and also over, of course, there's a gauge group in the bulk, but you don't gauge over the gauge parameters at the boundaries, because those are fixed by the boundary conditions on the gauge field. So you don't, but you do so what you basically get, because you do not integrate over the values of the gauge parameters at the boundaries, you have two independent global symmetries that arise from the gauge symmetry in the bulk. You can do an independent gauge transformation on the left and an independent gauge transformation on the right. And that's why the single global symmetry that you would have if the bulk had a global symmetry becomes two global symmetries. The difference is if you put two operators on the single surface and you have like a propagator that goes from one to the other, now these two gauge parameters at the endpoints are no longer independent, because you can deform this bulk propagator to become a line in the boundary that connects the 2 points. And that line tells you that the gauge parameters on the two endpoints have to be identical. So if you have like a Wilson loop between 2 points, and you can deform the Wilson loop to lie completely in the boundary, then the gauge parameters at the endpoints must be the same. But if the Wilson line has endpoints on two different boundaries, then the two gauge parameters are different, and you always get two copies of the global symmetry group. That's basically, if you think about that's really a more precise version, I think, of the argument.
Thank you. Thank you.
What am I doing? Yeah, so let me skip that. Let me just wrap up. You say that with OPE coefficients as random variables, we can model many aspects of a gravitational low energy effective field theory. And the key message was that this low energy effective field theory has access to the moments of these random variables, not to their individual values. And they gave you a perspective from the density matrix point of view, where we used moments of the density matrix, and they gave you a perspective from the operator point of view, where we used moments of the operators. All of that should fit in a single formalism. I'm still not entirely sure what that formalism is. It's also interesting whether these OPE coefficients are enough to capture everything if you go above 2 dimensions, because I wouldn't be surprised if, in order to be complete, once you're above 2 dimensions, you made line operators and so on as part of your complete statistical description. But I don't think we have a complete understanding of that right now. I try to be quite careful to be agnostic about whether the UV was averaged or not. And in some sense, it doesn't matter, because the required statistics could either come from coarse graining or from averaging. But importantly, there's no contradiction with anything that we know if it came from coarse graining. So there's no evidence here that your theory needs to be averaged. All the statistics could simply arise from coarse graining. It would be great to find a sharp diagnostic in the low energy effective field theory that distinguishes coarse-grained UVs from average UVs, but I'm not sure that that even exists in the first place. So as I said, it would be nice to combine this density matrix statistics with this operator statistics point of view. I mostly looked at these like Gaussian, so the second order moment as the most important moment, but there are higher order moments, and it would be nice to understand the exponential hierarchy between all these things and to understand better the nature of these things. It's also interesting that crossing symmetry relates light to light, heavy, right? You know, if one propagator gets short in one channel, it can get long in the other channel. So in some sense, if you write down the crossing equation between light and light, heavy, so a light intermediate channel versus heavy, one of these is statistical and the other is not in this picture. So it would be nice to see if there's like a more statistical approach to the whole Bootstrap program. Maybe in some sense, the entire Bootstrap program is already statistical, because I think typically what you get from the Bootstrap is things like sum rules, for example, for the high energy spectrum. If people do Bootstrap, for example, there's all these fun contour deformation arguments that are very often employed to relate UV to IR physics. But these contour deformation arguments, they never give you microscopic high energy information, certainly not if you're at large C and so on. They give you things like sum rules for the high energy states. And I think those sum rules are morally very similar to the statement that I'm making here, that the IR theory computes moments. Sum rules are also computing moments of high energy, you know, densities of states and so on, and other moments of high energy things. That's what sum rules are computing. They're not computing individual values. Now let me skip that all. Let me just maybe here. So it's an interesting question, almost like a bootstrappy type question, maybe. Maybe all that we have found here is that the low energy effective field theory in the bulk is the same as the low energy effective field theory on the boundary, where we also added crossing symmetry and modulum invariance. And then it really starts to look like some sort of bootstrap program. Maybe we should also add something like the large gap assumption and the non-existence of light spin 3 operators and so on, because we want to have a weakly coupled holographic dual. But other than that, I started to wonder, I added these sentences like a few days ago, because I start to wonder more and more whether this is really what we're seeing here. Crossing symmetry, for example, the fact that in one channel, the 4-point correlation function is simple, and the other channel, it involves a sum over heavy operators. It again gives some sort of sum rule for the heavy operators. In some sense, the first paper that pointed out that there was possibly a statistical nature of OPE coefficients, I think, was a paper by Slava Ryskov and friends, where they precisely looked at crossing, and they said that in order to to let the sum converge and possibly give the right answer, the OPE coefficients need to have the following sort of asymptotic behavior. So I wonder if this is at the end of the day the lesson of everything that I've been telling you. If so, that's interesting, and now we can try to think what we learned from it, but I think I'll stop here. Thank you.
Thank you very much, Jan, for a wonderful talk. And thank Jan. Questions?
Sorry, if I may go first, Abhijit, is it okay? Jan, that's a very beautiful talk. Thank you. And I really like the point of view you're giving here, that you might have wormholes, but it could be due to, some kind of UV coarsening. But how is it still? I mean, this is the question I'm really left with always, is how is the gravity theory, if it's doing some kind of coarse graining, able to give us the fine-grained entropy, as in the Ryu-Takeyanagi surface, or more recently, perhaps, the fine-grained entropy in the outgoing radiation? how does it manage to do that if it's averaging out the spectrum and so on?
Well,
Hello?
it gives some sort of fine-grained entropy,
Yeah.
but it doesn't give you. It's still an approximation to this fine-grained. I mean, it doesn't give you the exact fine-grained entropy, right?
Yeah.
It's still some approximation.
Yeah, it doesn't give you the exact S matrix or something.
No, it doesn't, and also it's called the fine-grained entropy for a good reason. But ultimately, the entropy is still a statistical object in some sense, right? Which we are computing.
Yeah.
And I don't think we can trust this, like the form of the page curve, the qualitative form of the page curve comes out correctly.
Mm-hmm.
But then, for example, I think in JT gravity, people studied in detail sort of what happens near the turnaround point and try to resum wormholes to smooth out that transition between the and the rounding. And I think that's those are computations you can do, but you're still doing some sort of 1/n expansion of some sort or another. Mm-hmm. Mm-hmm. And it's interesting that at the end of the day, you can predict that something becomes a pure state, but that's a gravitational observation because the black hole is gone. Gravity knows that you had a pure state at the end because like the black hole is gone to some extent, right? So
you do better than that. You see the.
No, I know.
Yeah. Okay.
No, I have to say this is why I mentioned this first point. So I think the curve itself, that's a coarse-grained feature. Yeah. It's a coarse-grained aspect of this fine-grained entropy computation. Maybe what the puzzle is why you can reliably argue it goes all the way down to 0 at the end.
Well, you even start seeing the fact, I mean, the fact that it's it's coming down and not going up, like Hawking said, is already because you're seeing a fine-grained entropy, right? I mean, gravity seems clever enough to detect the island, as they call it now. I mean, it's
how well
spectacular, no? I mean, if it were just coarse training, it could have.
Well,
yeah, I don't have a precise question, but yeah.
No, but it's a good question, and maybe to answer this question more precisely, we should couple the CFT to an auxiliary CFT and really emulate the system that we're trying to describe. Because without this coupling, I think one of the lessons is that simply the sharp separation between the black hole and the radiation mathematically somehow does not exist, right? So there's no, the Hilbert space does not factorize. In fact, the island shows that it does not factorize. So if you wanted to set this up more precisely in a field theory, we should probably really model the whole page curve computation more precisely. And maybe if we couple the CFT that's dual to the bulk to this auxiliary BAF CFT, and we set up these statistical computations, treating the BAF microscopically, right? Because that's crucially what is being done in these computations. Right. If we glue a statistical CFT to a microscopic theory, maybe we will see exactly the same feature. And then I would be happy.
Yeah. Okay, good. Yeah, that's a nice way to put it. Right. I see. Okay, thank you.
Yeah, Jan, could I ask, you had this way of understanding how you could compute finite temperature endpoint functions from this ETH sort of viewpoint. Let's say in a 3+1 dimensional field theory like n = 4 angles, could one use that to find the detailed form of the thermal two-point function of two operators? As you know, it's a very complicated answer. It has all these quasi-normal modes and
in that sense, I don't think this formalism is very predictive. In ETH is not really does not predict the form of these two-point functions.
Why not? Where does it? At what stage do you need extra information?
So ETH is this statement. So there is this delta ij piece. But then there is this piece that is this E minus S over 2. And then there's a function that's a function of the average energies and the difference of the energies. And then there's this random matrix. But this function G is not, there's no prediction what G is. The only statement is G is some smoothly varying function of the sum and the difference of the energies of E and omega, if you wish. And now this G has exactly the same amount of information as the finite temperature 2-point function, because crudely speaking, the finite temperature 2-point function is some sort of Fourier transform. It's not literally a Fourier transform, it's more complicated, but some transform of G.
Okay. So though there was no predictive power for one theory, you were able to get predictive power when you had now two theories.
That's right, yeah.
So, but in the one theory example, there's no prediction. This whole way of thinking makes no prediction at all. No testable prediction.
Well, in the two product
case, yeah, and not that I've been able to come up with, but for example, yeah, if you do the two theories, this would predict that this in some sense seems to predict that if you do the following computation, you take a thermal circle times the 3-sphere with 2 operators on it, and another theory at finite temperature for n equals 4 super Yang mills in S3 with 2 operators on it, there would now be this other Wick contraction between these random variables. So you might think that there is some sort of wormhole, even in AES5, that connects these two things.
So isn't it true that it's giving the classical action of the wormhole in some sense?
That would be then the non-trivial prediction / computation to do. Now you have to be a bit careful, because maybe maybe there's a higher order moment that is also important that you cannot completely ignore and so on. But in principle, these are the types of games you can play.
So but it predicts completely what you would get in the two theory example if you knew everything about the one theory example. Is this right?
Sorry, say again.
So suppose you've got two. Suppose I know everything about n equals 4 Yang mills at finite temperature. I know all the correlation functions. Somehow I've computed them. Now I take 2 n equals 4 Yang mills with let's say with an S1, and then this formalism of yours, can I view it as a machine that will take the known answers for one theory and spit out all the answers for two theories?
Yeah, it makes predictions about the connected 2-point function between two theories and the gravitational approximation. Yeah.
Right. So, but everything about that. Right?
Yeah, all the low energy stuff might. Yeah, you may wonder. Yeah, that's right. That's what seems to be the prediction that one is making here. Right.
So, if I could tell you all about how the gravitational solution with one S3 times S1 boundary, you are able to generate everything you'd ever want to know about gravitational solutions with 2 S3 times S1.
Yeah, that would be great if that were true. Yeah, that's pretty much the proposal to say. Yeah, that's right.
Sorry, giving you the relative strength between the connected piece and the disconnected piece, and not absolute things. I mean, not the absolute.
Well, in general, there will be an exponential hierarchy between the two.
Yeah, and this will give you the hierarchy, right? Well, I guess
this will give you, yeah.
But if you knew the one boundary thing, you knew the the disconnected things.
Square of that.
This now tells you what the connected things are.
Yeah.
Right. So, okay. One more question, please, Jan, if you don't mind. It's different nature. You talked many times about this UV smearing of the theory. Now, suppose I handed you, everything you want to know about n equals 4 Yang mills on S3. Okay, everything about it. Now, what is the systematic procedure one would use to get this smeared? Could you say a little more what you mean by the smeared theory? I mean, is there some systematic procedure, something that we are used to doing that gives rise to the smeared theory?
Yeah, I'd love to give you a precise answer, and to do that in an actual setup and do the precise computation. The precise nature of the smearing may well depend on what you call the low energy effective field theory. So morally speaking, I probably have some sort of microcanonical unitary averaging of the high energy degrees of freedom in mind. But I don't have a precise answer to this question.
So what,
ideally, we can identify like a toy model or some other system where we can check these things in more detail, but I don't have that. I don't know precisely what that smearing is. No, I don't. Except that it's some smearing, but I don't have a precise microscopic answer what it could be.
sorry, but what is the definition of these smeared objects? Is the object which produces the right correlation functions in the effective low energy supergravity, right? That kind of.
That's right. Yeah. Yeah.
That you can think of it as some sort of a derivative expansion, and then that would be the way of defining these smearings, right? Like what kind of smearing would give rise to the right answer in a given derivative expansion? Is that how one would make this precise? Or I mean,
but it would be much more satisfying to have a high energy way of thinking of it rather than going the answer and back calculating.
No, but I'm just saying by definition, this is the kind of object you want.
Yeah.
Which is correct to some order in derivative, which would produce the right answer to some given order in derivative expansion. What would be the smearing?
Yeah.
That's right, and that's a great question. But I don't know what is the best way to start tackling that question. No, I think these unitary. The technically speaking, the simplest thing that you can actually do is this version of unitary averaging. But whether that's really the thing that you that gives this structure on the nose, or whether you just give something that's qualitatively similar, is not so clear to me.
But Jan, I was also thinking like Abhijit that, okay, after all, we are going to do renormalization group to construct the low energy theory, and those heavy loops you were talking about, basically your averaging is some way of, replacing the detailed particles running in that loop with some, effective density of states, etc., which reproduces the low energy correlator, right?
Yeah.
And then you just sort of try to get away with the least amount of information about the high energy theory to get the vertices of the low energy effective theory right. Something like that.
That's right. Yeah.
Would we do it in some simple matrix model which has two scales?
Yeah, those are all great questions. Sometimes this whole story reminds me somehow of the classical limit of quantum mechanics, which is really only well defined if you take an h bar to zero limit. Mm-hmm. But if you keep h bar small and finite, it's very murky. Exactly what you mean by the classical limit. In some sense, it's really, strictly speaking, only defined as a limit. And then in the high energy theory, there's many different like wave functions and wave packets that you can choose that in the h bar to zero limit all give the same classical physics. However, there are these nice distinguished things in like coherent states that are kind of nice. So there are nice, if you wish, quantum states to use that seem to be preferred to give classical physics. Maybe there's a version of that here. I don't know what it is, but in some sense, what I would do is I would probably define the smearing as the most general smearing that is consistent with the low energy information.
Yeah.
In some sense, we sometimes try to play this game in AGS-CFT where we say, suppose I fix all the 1-point functions in some region, and I find the density matrix with the largest entropy that gives the right 1-point functions. Am I then somehow computing like the area of the entanglement wedge minimal surface? And that doesn't work, but questions like that have been asked in the past. And maybe like coherent states are those states that minimize something, and maybe there's a version of that here as well, but I don't know what the answer is. No.
Shouldn't n enter into your answer somewhere?
Yeah, that's the h bar. That's the h bar of quantum mechanics. I think the n here plays the same role as h. So we have to do something like the classical quantum transition, but now with n instead of h bar. Yeah.
Right. Yeah, large n seems really crucial. I don't know. Yeah. I see.
One question regarding this. So what I said about this derivative expansion, I was thinking of low energy theory as some theory of low energy modes in some derivative expansion, but these coarse grained quantities are not addressing light OP coefficients anyway, right? They are addressing OP coefficients which involve one of the, at least one heavy operator.
Yeah, because the light ones, they're just part of the low energy effective field theory on the boundary already, right? So we don't, those are also there. Those are also part of the theory, but those we assume we know. Yeah.
So the coarse graining that is involved should be done in such a way so that it produces the right correlation functions in the background of black holes and things like that. I guess
that's right. Yeah.
Not just this. Yeah.
That's correct. Great. Thanks for the many questions. Are you frozen?
Sorry, one more question. The last point that you were making about coarse graining of the heavy stuff, because here a priori the proposal of yours doesn't quite say that. I mean, the low energy effective bulk theory should be dual to low energy boundary theory, right? Because so in other words, in boundary theory, why is it that I should not expect from the bootstrap equations precise microscopic data? Because that's the kind of thing that I thought you were trying to say, that actually the bootstrap equation will give you some coarse grain answer, but that is an independent claim compared to the one that you made about this one, right? I mean, the gravity theory. Is this
I mean, of course, like if you bootstrap a theory with small central charge and so on, then maybe it's a self-sufficient set of equations. But if you do bootstrap at large n, then I think it's at best going to give you statistical high energy information as well. Yeah.
But I could go theory from there also. Why not?
Sorry, you could?
Yeah, I mean, but I mean, a priori you're saying, is there a why is it that the bootstrap program should see only the low energy effective field theory in the bulk?
I don't know, but that's somehow you could use that as input for your bootstrap. You have to put some input. Like typically, if you bootstrap, what do you say? Well, let's assume we have one scalar, and with some conformal dimension d, and it has a bound state or something, and there's some other conform. You put some minimal low energy ingredients in your bootstrap program, and then you see what comes out as possible solutions. If you stick in the low energy information of the theory that you know, and now you ask, like, is there like a completion of this? What, I'm going to impose modular invariance and bootstrap. It's like the Cardy formula that just follows from modular invariance and just the ground state. So sometimes you need very little low energy information to get high energy information. If you want to have corrections to Cardy, you need to include some light operators, and you do the modular transformation, and there's all this Tauberian theorem stuff and so on. You can get corrections to the Cardy formula. So it's all very similar to what goes on in Bootstrap, I think. But this would be, and I think in large and Bootstrap, I imagine, some rules and stuff.
Thank you.
Sorry, just one more follow up on that. The kind of sum rules that you're talking about also appear in S matrices when we study S matrices, but they appear just in ordinary quantum field theory S matrices, not necessarily in theories involving gravity. However, for you, somehow gravity was very important, right? So I was wondering, I don't want to use ADS EFT there because their gravity is somehow very natural because there's a stress tensor on the boundary. So, but if we just use the flat space S matrix, should there be some special features that come out when we study the flat space S matrix bootstrap program involving gravity that are not there without gravity? Would that be your expectation?
Okay, that's a very different question, because now I was really imagining applying bootstrap to the boundary CFT and not in the boat. So if you start to bootstrap a theory with gravity, then that's, I think, a different game than what I'm talking about.
I see. So
yeah.
Right. You're going to do it on the boundary, and there gravity is automatic because your boundary has a stress tensor. Right?
That's right. Yeah. But doing the type of bootstrapping where you start with the low energy graviton S matrix and try to ask about UV completions of that's I think a different type of question than what I'm asking here. I think that's really maybe there's an interesting connection.
it may not be so different in the end, because sort of like an S matrix is what lives on the boundary of flat space, just like correlation functions live at the boundary of ADS. May not be too different.
No, that's right. Maybe some interesting lesson. Yeah.
Okay. No, but thank you very, very much for a very, very interesting talk.
Yeah, can I ask a question? Just yeah. So Jan, can I ask?
Yeah. May I? But may I suggest this is the last question, because I have like a long, annoying administrative meeting in 6 minutes. So.
Okay. All right. Yeah. So it's a little perhaps a vague question. So so in a normal, non-gravitational quantum field theory, you can say that the UV degrees of freedom decouple because they are represented by irrelevant operators. So if you do Wilsonian renormalization group calculation, and so here because of the random averaging, perhaps over the 3-point couplings and so on, is it that they are not quite irrelevant operators, in the sense that I mean, it's a vague question. You turn on the usual thing of Wilsonian renormalization group, but you also do this averaging thing, and somehow the irrelevant operators do not quite decouple. Is there something like that's possibly going on? But only some limited amount of information.
Yeah, I haven't thought about that. Like the same phenomena that in if you do disorder average, that it changes the dimension of operators from an operators that seem to be irrelevant can become irrelevant, or the other way around if you do disorder averages, right? What is it? Is Harris criterion and so on. Yeah, I haven't thought about it in this context. Yeah, it's an interesting question. Okay, whether that has any bearing. I haven't thought about it in this context. I'll think about it. Thanks. Yeah.
Okay.
All right, Jan, thank you very much for your talk. Wonderful talk, and thanks for answering the questions so patiently. Thanks.
Thanks so much, Jan.
Thanks, guys. That was fun. Hope to see you in person sometime somewhere. Take care. Ciao.
Yeah.